Hi guys, welcome to the chapter on chemistry, specifically the chemistry of life. The beginning of the chapter will always again start with objectives. I'm not going to read them all to you, but these are things that you should be able to do by the end of the lecture. You can use these to guide your studying until you get the study guide. So we'll start our discussion of chemistry with some basic terms, beginning with matter. Matter is everything around us. Anything that takes up space or has mass, no matter how small that mass is matter. So I am matter, you are matter, the computer, the air around us, the water we drink, food we eat, this desk, everything is made up of matter. Now, matter is made of tiny, tiny little structures called atoms. Okay, billions of atoms make up a cell. An atom is the smallest stable unit of matter. Now, when we use the term atom, we could say 1 atom of hydrogen, 1 atom of carbon, 1 atom of oxygen. What that means is that it's 1 single unit of oxygen. Atoms are tiny, right? Much smaller than you could see, even with a microscope. They're very, very small. But they join together to create everything, right? To create you and me. So they must be able to join together to make larger things. And it's interesting because when atoms join together, they form new chemicals that can have completely different characteristics. For example, if we have plain hydrogen, it's a gas. If I have plain oxygen, that's also a gas. But if I put those two gases together, right? If I put 2 atoms of hydrogen with 1 atom of oxygen, and those atoms join together, if they bond together to form a larger compound, all of a sudden this new compound behaves completely differently. Now, instead of 2 gases, I have 1 single unit of H2O, which you guys probably recognize as water, right? This is a liquid at room temperature. So it's important to know or to understand how it is that atoms combine with each other and what types of characteristics they have, because that influences what they do in our body or how they behave in our body. The chemical characteristics of the atoms that are present in our cells are going to determine the physiology of that cell or that molecule. So they are important for us to learn. It's a little cumbersome, a little challenging typically for students to get through this chapter, but we're going to learn extremely important concepts in this chapter. Understanding how a lipid works or behaves, for example, is going to tell you how it travels through the bloodstream, how it enters into cells. Understanding the structure of a protein is going to tell you a lot about the way things move in and out of the blood, or whether or not things get filtered out of the kidneys. These things that we're learning now in this chemistry chapter might not seem like they have anything to do with the human body to you right now, but I promise you that they do. All of these characteristics that we're going to learn in this chapter are going to go on and tell you how things behave in the body. So they are incredibly important for you to learn. So bear with me. All right, so matter refers to anything around us, right? Anything that has any sort of space is referred to as matter. And we said that matter, so everything, is made up of atoms. An atom is 1 single unit of an element. So 1 single unit of hydrogen or 1 single unit of oxygen. Now, atoms are made up of subatomic particles, right? So subatomic, like parts of the atom. There are 3 different subatomic particles that can go into making an atom: protons, neutrons, and electrons. Okay, so atoms are made up of protons, neutrons, and electrons. Each of these has their own specific characteristics, right? So a proton, neutron, and electron, they could have some weight, some size, and they could have a charge. They might be positive, negative, or neutral. Now, different kinds of atoms have different numbers of each of these. That's how they're different from each other. This is what makes a hydrogen atom different from a carbon atom. It has a different number of protons. Now, when we look at these subatomic particles, it's important that you understand the characteristics that go with each one of these. Protons are located in the nucleus of the atom. If you look over here, you can see kind of like a general structure for what an atom looks like. In the very middle of the atom, this area right here, this is called the nucleus. That's like a really dense, heavy core. That's where all of the actual mass and weight of the atom is, in the nucleus. So the nucleus, the core of the atom, houses protons, and then you'll also see that there are neutrons in the nucleus as well. Right, and looking at this picture, you can see that, right? The nucleus is made up of these little red dots and the white dots. And you see here that those are protons and neutrons. So protons and neutrons are in the nucleus of the atom. And then out here, these little blue structures that you see, these are called electrons. Electrons are not in this dense core, this dense nucleus. Instead, they're constantly, really rapidly moving around or orbiting around the nucleus in something called the electron cloud. Right? So that's the general structure of what an atom is going to look like. Made up of protons, neutrons, and electrons. Different types of atoms have different numbers of these things. The protons and neutrons are in the nucleus. The electrons are constantly moving around in the electron cloud. So let's look at the characteristics of each of these particles. Protons have a positive charge. So match up your P's, right? Protons are positive. So every proton that an atom has brings one positive charge. So if you have an atom that has 6 protons, that means it has 6 positive charges. Every proton also brings 1 mass unit. So again, if you have 6 protons, then you're bringing 6 mass units to the atom. You can think of mass like weight. Technically, there is a difference in their description because weight implies gravity, but don't worry about that. Just think of their mass as like their size and their weight. All right, so protons are positive and they have some weight to them. They have some mass. Neutrons are neutral. What that means, what neutral means is no charge. So they're not positively charged, they're not negatively charged. They're neutral, hence the term neutron. But they do have some mass to them. They do have some weight. Every neutron contributes 1 mass unit to the atom. Okay? Finally, we have electrons, those things that are always moving around, orbiting around in the cloud. Electrons have a negative charge, so they're opposite of the protons. Protons are positive, electrons are negative. So every electron that an atom has brings 1 negative charge. Electrons are tiny. They have such a low mass that it's negligible. We don't even count it. It doesn't matter. It doesn't have any impact at all. Okay, so we don't worry about their weight or their mass when we're talking about how much an atom weighs. So looking at this right here, I could say, if I am looking at an atom, right? I have this atom right here, and I want to know how much does that weigh? What's the mass of that atom? How big is it? I'm going to look at 2 things. If I want to know what the mass size of the atom is, I'm going to look at the protons and the neutrons. Both of those were the ones that have mass. So the mass is going to be the number of protons plus the number of neutrons. If I want to know the charge of the atom, right, is it neutral? Do the positives and negatives cancel out? Is it more positively charged or is it more negatively charged? If I want to look at the charge, I'm not going to worry about the neutrons because they're neutral. For charge, I'm worried about the protons and the electrons. So the charge is the number of protons, those are all positive, minus the number of electrons, because electrons are negatively charged. Okay, if they have the same number of protons and electrons, those will cancel each other out, right? 6 positives, 6 negatives brings us right back to 0. That's neutral. Okay? If they're not the same, then the atom will end up having a charge, either a positive charge or a negative charge. Okay, we're going to end up working through a lot of different examples where we'll look at an atom and figure out how many protons, how many neutrons, and how many electrons it has. So you're going to end up getting a lot of practice with this. So just kind of bear with me, work through it with me, and by the end you should be really comfortable. All right, so elements, right? An element is the most basic chemical that exists. Elements are pure substances that contain only one type of atom. So you can have a lot of atoms, but they're all the same. So carbon is an element. Hey, I could have 1 atom of carbon. I could have 100 atoms of carbon. I could have 1 trillion atoms of carbon. But if it's all carbon, it's pure carbon, that is the element carbon. Or pure oxygen. Oxygen is an element. Pure hydrogen. Okay, hydrogen is an element. If you guys think back to high school chemistry when you looked at the periodic table of the elements. The periodic table of the elements is a little table that contains little squares that represent each of the elements. Again, hydrogen, carbon, oxygen, sodium, calcium, these are all elements. When we look at an element is determined by the atomic number of the atom. So if it's atomic number 1, it's hydrogen. Hydrogen correlates with atomic number 1. Atomic number 6 is carbon. Okay, when you look at the periodic table, each of these little squares will have a symbol in the middle for the element. So that's the symbol for hydrogen. Up at the top, you'll see the atomic number. So hydrogen, for example, which you see here, is atomic number 1. I'll tell you that atomic number tells us something about the hydrogen, which we'll talk about in a sec. At the bottom, you'll have the atomic mass. So that's the average weight of all of the hydrogen that exists in the world. So the average weight is like 1.00794, I believe, if I'm remembering that correctly off the top of my head. Hey, that's the average weight of hydrogen. So about 1, if you rounded that off, right? Here underneath that, you see that the element lithium is atomic number 3, right? So you would have a square that has Li. At the top, it has a 3. I'm not sure what the weight of lithium is. So the atomic number tells us something about that element. The atomic number tells you the number of protons that every atom of that element has. Okay, so hydrogen. We said hydrogen was atomic number 1. That means that every atom of hydrogen has 1 proton. Always. If it does not have 1 proton, it is not hydrogen. Okay, the number of protons that are present in that atom will never change. In a little bit, we'll see that atoms can change electrons. They can give electrons away. They can take electrons. Sometimes there's different atoms of an element that have a different number of neutrons, but the number of protons is not going to change. Okay, if it is hydrogen, it has 1 proton always. We said lithium, right? I just told you guys up here that lithium is atomic number 3. So what does that tell you? That tells you that lithium has 3 protons. Every atom of lithium in the whole wide world has 3 protons. Okay, if it doesn't have 3 protons, it's not lithium. Carbon. Okay, carbon is something that's really common in the body. Carbon is atomic number 6. So every atom of carbon has how many protons? 6. Now, actually, before we talk about isotopes, before I talk about this page, let's talk about electrons really quick as well. So when we first look at an atom, before anything has happened to it, before it reacts with anything, before it mixes with anything, the basic element is neutral, right? It has no overall charge. What that means is that the positive charges must cancel out the negative charges, right? They have to be the same. And remember, protons are positive and electrons are negative. So what that means is that our basic elements, before they react with anything, they have the same number of protons and electrons. Okay? Later on, they can change electrons, but to start, they have the same number of protons and electrons. So while the atomic number tells you the number of protons, it's also going to tell you the number of electrons. Okay, so we can use atomic number to tell us the number of protons that are present and the number of electrons that are present. Now, all we have left to figure out is neutrons, right? If I know how many protons, and then I can use that to find out how many electrons, now I just need to know, how do I find out how many neutrons there are? Okay? And the way we find out how many neutrons there are is by looking at the mass of the atom, or the overall weight of the atom. So hydrogen, for example, we just looked at hydrogen. Remember, I told you that hydrogen is atomic number 1, and its mass is 1.00794 or something like that. So that's about 1, right? So let's see how many protons, neutrons, and electrons. Its atomic number is 1, so that tells me it has 1 proton. And because it's going to cancel out, the protons and electrons are going to cancel, it must also have 1 electron, right? Because it's got 1 positive charge and 1 negative charge. Now I just need to know, how many neutrons does it have? I told you guys we're going to use the weight down here to figure that out. Its overall mass, remember, is protons plus neutrons. Those are the 2 things that have weight, protons and neutrons. So if the weight is 1, and 1 equals protons plus neutrons, we know it has 1 proton. That never changes, right? So 1 equals 1 plus what? 0. Okay, so that means that hydrogen has 0 neutrons. So most atoms of hydrogen that you find in the world will have 1 proton, 1 electron, and 1 neutron. Now, in a little bit, we'll talk about how it can react with things to change its number of electrons, right? But otherwise, this is what hydrogen will look like. Now, if you notice this mass number that we have down here in the bottom, this 1.00794, that is not a whole number. We rounded it to 1, right, to make the math easy, but if you look at that, that is not a whole number. And the reason is that I told you this is the average mass for all hydrogen that exists in the world. So that means that there must be some hydrogen that actually weighs more than one. Not very much of it, but there is some hydrogen out there, some atoms of hydrogen that are kind of heavy, that weigh more than one. Okay? Now, the reason for this is because there are different versions of each element, and those are called isotopes. So that brings us to this slide. Isotopes are the different versions of an element based on its mass number or based on its weight. So the mass, remember, equals the number of protons plus the number of neutrons. Okay, electrons are tiny. So when we look at the mass number, when we look at the weight of an atom, that's the number of protons plus the number of neutrons. Now, different isotopes or different versions of an element have a different mass, they have a different weight because they have a different number of neutrons. So if I have two versions of hydrogen, one of them weighs 1 mass unit and the other one weighs 2 mass units. That second version, that second isotope of hydrogen is heavier because it has an extra neutron. Okay, remember, the number of protons is not going to change. Protons determine the element. If it is hydrogen, it must have 1 proton only. That's not going to change. So if I have hydrogen and it's heavy, it weighs 2 mass units, that means it must have an extra neutron present. Okay, so there are different versions of each element. They have a different mass. The reason their mass is different is because they have a different number of neutrons. We call those different versions isotopes. The atomic mass on the periodic table, remember that's this one down here. I told you guys that that shows the average mass of all isotopes or all versions of an element. Right? That's why it's not a whole number, because every once in a while we'll come upon an atom of that element that weighs either a little bit more or a little bit less than most of the others. Okay, so here we see this example of hydrogen kind of spelled out for us. These are the different isotopes, right, or versions of hydrogen that exist. So each of these pictures, each of these is showing us a type of hydrogen that exists in the world. Okay, this first one right here is normal hydrogen, typical hydrogen. Hydrogen 1, it has a mass number of 1. That means that this atom weighs 1 mass unit. When we look at it, when we look at the way that the atom is structured, you see that it has 1 proton in the center, right? We know it has 1 proton because it's hydrogen. Hydrogen is atomic number 1. It always has 1 proton. And then out here in the electron cloud, you see that it has 1 electron. That's good because remember, they should cancel each other out. The number of protons and the number of electrons is equal. The positives and the negatives cancel. The mass is 1, and remember the mass equals protons plus neutrons. So 1 proton, 0 neutrons, 1 plus 0 equals 1. That's how most hydrogen is in the world. Rarely, every once in a while, there's hydrogen 2. Okay? This hydrogen has a mass number of 2. Okay? It still has 1 proton because it's hydrogen. It still has 1 electron, right? Because the protons and electrons have to cancel. But now we see that it also has 1 neutron. Okay, that's how it gets to a mass of 2. Again, the mass equals protons plus neutrons. So 1 proton plus 1 neutron. Then even more rare than that is hydrogen 3. It has a mass of 3. Okay, so if the mass of 3 equals the number of protons plus the number of neutrons, okay, and we know that the number of protons never changes, so the mass of 3 equals 1 proton plus How many neutrons must this have? 2, right? 2 plus 1 is 3. So if you look here in the nucleus, notice it has 1 proton and it has 2 neutrons. That's how it gets to a mass of 3. It's heavy because it has more neutrons. So these are all the versions of hydrogen that exist. These hydrogen 2 and 3 are really rare. Most hydrogen does not look like that. When we average all the hydrogen in the world together, the average mass is 1.00794 because of the rare situations where every once in a while we have a heavy hydrogen that exists. These are the main elements that exist in the human body. You see the element listed, right? And then you see its symbol next to it. So oxygen is an O, carbon C, hydrogen H, etc. And then the number that you see tells you what % of the human body is made of that element. So you can see that oxygen is by far takes the most weight present in the human body because our body is mostly water, and water is H2O. And oxygen's a lot heavier than hydrogen. So most of the body is oxygen, followed by carbon, hydrogen, nitrogen, calcium, phosphorus, potassium. But really these first few, oxygen, carbon, hydrogen, and nitrogen, are the most common elements that we have in the body. These are what we call trace elements down here at the very bottom. These are things that are present in like tiny little amounts in the body. And then you see just these are some other ions that will be present in the body, or like electrolytes that will be present in the body. I don't expect you to memorize anything from this. This is just kind of FYI. These are the elements that we actually see in humans, because not all elements are present in humans, but these are the ones that you do see in humans. Okay, so we're going to spend a little bit more time talking about electrons because electrons are very important in determining how an element behaves or how a molecule behaves. We said that the protons and the neutrons affect the weight or the overall size of the atom, but when you want to know what that atom's actually going to do, you look at the electrons. Okay, so we say that the electrons in the electron cloud, right, the electrons that are floating around out there in the cloud, determine the reactivity of an element. Okay, they determine the reactivity. So reactivity, again, is like behavior, right? How it reacts. If I put two atoms together, how are they going to react to each other? Are they going to bond and form something stable? Are they going to blow up? How they're going to react is determined by the electrons that are present. So when we look at the electrons, we know that the electrons are floating around in the electron cloud, right? Now, when we look at that electron cloud, it's not just one big space with all the electrons crammed in. The electron cloud contains electron shells or energy shells. And think of them kind of like the floors on a house, right? You have the first floor, and then you go up, you use energy to go upstairs to go to the second floor. And then you use more energy to go up to the third floor and more energy to go up to the fourth floor. That's how these electron shells are. There are different floors or different levels, and it takes more energy to go out further and further and further. Now, each of these electron shells holds a maximum number of electrons. So you can't just cram them all into the first shell because it's easiest. Okay, the first shell only holds 2 electrons. So you put your first 2 electrons in there, but if the atom has more than 2 electrons, well, the next ones have to go up to the next shell. Now, there are some elements that are huge, right? They've got a ton of electrons, but most atoms that are present in humans only have up to the first 4 shells. We're really just going to look at the first few shells so you can kind of get an idea of the way that this works. If you take chemistry, you'll go through this in way more detail. I just want you to have kind of a glimpse of this idea. We'll talk through these few rules right here, and then bear with me. We're going to go through quite a few examples, and then this will all start to make sense to you. So just kind of roll with it for now. Now, an atom only has the minimum number of shells that it needs to hold its electrons. So hydrogen, for example, has 1 electron. That means it only has the first little shell, right? It doesn't have empty shells. So if I had, just me living in a house, I don't need 10 stories to house myself. I just need 1 story. I just need 1 floor. So atoms only have the number of shells that they need to hold their electrons. Also, the shells fill in order. The lower shells fill first. So the first electron shell will fill up with its 2 electrons. And then the second shell will fill up with up to 8. And then the third one will fill up with up to 8. Okay, so they go in order. Finally, the outermost shell that an atom has is called the valence shell. This is the shell that's important. The electrons that are in this outermost shell are going to determine the bonding or behavior of the atom. So the valence shell is different in different atoms. If an atom only has 1 shell, that's the valence shell. Because remember, it doesn't have any empty ones, so that's the outer shell. If it has 2 shells, then the second shell is the valence shell. If it has 4 shells, then the 4th shell is the valence shell. Okay, so the outermost shell is the valence shell, and the electrons that are present in that outermost shell determine what the atom is going to do, if it's going to bond with another atom or not. Okay, the reason for this is that atoms want a full valence shell or outermost shell. Atoms are happy when their outer shell is full, and they will react with other atoms to try and fill up their outermost shell. This is how atoms end up joining together to form larger things, right? So this is why if I have 2 hydrogen and 1 oxygen and I put them all together, they're going to join to each other, right? They're going to bond with each other because they're all trying to fill up their valence shell. So we're going to do a few little exercises here just to kind of start placing electrons in electron shells so you can see just kind of how this works, how the electrons will fill the shells. So we see 2 atoms, right? This is an atom of hydrogen, and this is an atom of helium. Hydrogen is atomic number 1, and its mass number 1. So let's see, what does that tell us? It's atomic number 1, so that tells us it has 1 proton. Protons are positively charged. If it has 1 positive, it must also have 1 negative. So that means it also has 1 electron, which is a negative charge. Its mass is 1, and the mass, remember, equals protons plus neutrons. So if the mass is 1 and it has 1 proton, it must have 0 neutrons. So if we were to map that out, right, and draw that atom, here you see it has its 1 proton in the nucleus in the middle, and it has its 1 electron out here in the electron shell, in the electron cloud. Now remember, we're talking about shells. Which energy level or shell do we put that in? We're not going to draw all these shells and throw it out here in the 3rd shell, because remember, the electrons go into their shells, the 1st shell, then the 2nd, then the 3rd. They fill in order. Okay, since there's just 1 electron, we're going to put it in this 1st shell, and that's what hydrogen looks like. The 1st shell can hold a maximum of 2 electrons, so hydrogen could actually fit 1 more electron in that shell. Helium, you guys see over here. Helium is atomic number 2, and it has a mass of 4. So let's see, what does that tell us? The atomic number of 2 tells us that there are 2 protons and 2 electrons. The mass is protons plus neutrons. So if the mass is 4, that means we have 2 protons and 2 neutrons. So 2 protons, 2 neutrons, and 2 electrons. We know that in the center of this, in the nucleus here in the middle, that's the nucleus, that's where we have our protons and neutrons. So there are 2 protons and 2 neutrons, all heavy in the middle. Now, if we're going to place our electrons, we have 2 electrons to place in the cloud. We said that this first shell right here can hold 2 electrons. So that's perfect. We put 2 electrons there in the first shell. And remember, I told you guys that atoms will do things. They'll behave to try and fill their outermost shell. Well, helium already has a full outermost shell, right? This first shell is its outer shell, right? That's the valence shell. And in this case, the valence shell is full, without helium having to do anything. It doesn't have to bond with anything or react with anything. It naturally has a full valence shell. That means that this is a really stable atom. It doesn't really react with much because it's perfectly happy on its own. Now these 2 right here, let's do 2 more examples so you're really comfortable with it. These atoms are a little bit bigger. So now we're going to have to move on from the first shell. We're going to have more electron shells to hold more electrons. Lithium is atomic number 3, right? So that tells us it has 3 protons and 3 electrons. Its mass is 6, so that means it must have 3 neutrons as well. Okay, hopefully that's comfortable. You understand how to figure that math out. So we need to place these 3 electrons. Okay, how many can we put in the first shell? 2, right? We can only put 2 electrons in the first shell. So you see here's 1 and here's 2. We still have 1 electron left. We can't cram it in that first shell. It's already full. So that means there must be another floor, right? There must be another level out there. So here you see the second electron shell. Now we put our 3rd electron out there. And this is what lithium looks like. This second shell and the 3rd, just because of the way things fill, can hold up to 8 electrons each. So the second shell can hold 8 electrons and the 3rd shell can hold 8 electrons. So if we look at this lithium right here, lithium has 1 electron in this second shell, and this shell can hold 8 electrons. So lithium is not happy, right? He's really reactive because this outermost shell is not full at all. It's not even close to being full. So he really wants to do something to try and get a full valence shell. Now, we'll talk about what he would do in a second, whether he would gain an electron or lose an electron. This over here is neon. Okay, neon is atomic number 10 and its mass number is 20. So pause the video, take a second, and I want you guys to figure out how many protons, how many neutrons, and how many electrons. Okay, and then press play and we'll move forward. So the atomic number of 10 tells you that there are 10 protons, right? 10 positives. And because the positives and negatives have to cancel out, that means there must also be 10 electrons. If the mass is 20, remember that equals protons plus neutrons. So mass of 20, we already know there are 10 protons. So 20 equals 10 plus 10. So there's also 10 neutrons. Hopefully you got that perfectly fine. Now, now we need to place these 10 electrons. Hey, how many can go in the first energy shell? 2. So we put our 2 electrons here in the first shell. Right? We had 10 total, so now we have 8 left. How many can we put in our second shell? 8. Perfect. Right? So we put our 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 in our second shell, and neon has a full valence shell. Right? The second shell can hold 8, and it has 8, so its valence shell is full. Do you think that neon is highly reactive, or is it really stable? Does it not interact with anything else? Hopefully you said it's stable, right? It's already happy. Its valence shell is full. It doesn't have to do anything. It doesn't have to interact with anyone else because it already has its valence shell full. So neon and helium, these are what we call the noble gases because they're all very stable. They all have a full valence shell. Okay, so who cares, right? Why do we care about any of this? Why do we need to know where the electrons are or what the valence shell is? The reason is because, remember, I said that the electrons in the valence shell determine how the atom, or if the atom, will bond with other atoms, right? Is it going to join with another atom and build something bigger or not? Every chemical reaction that occurs in your body occurs because of electrons in the valence shell. Every reaction, our entire metabolism in our body happens because of these electrons in the valence shell. So let's talk a little bit about these chemical bonds. A chemical bond is the joining of 2 or more atoms to make a larger, more complex structure. Hey, this is how we are made. We're made of lots and lots and lots of chemical bonds, joining together trillions of atoms until we have these large things that are visible and tangible. Now, a chemical bond, this joining of atoms, occurs because of either the sharing of electrons, so when 2 atoms come together and share electrons with each other, or the gaining and losing of electrons. So when 2 atoms come together and one of them says, hey, I'm going to take your electrons, and this one says, okay, great, bye, you can have them. Okay, so 2 atoms come together and they either share electrons or they take and give electrons. That forms a chemical bond between those 2 atoms that holds those 2 atoms together to make a larger structure. Now, again, the reason that this happens, the reason that atoms will trade or share the electrons in their valence shell is to try and fill up that valence shell. Atoms want a full outer electron shell, a full valence shell. That's when they're happy, right? That's when they're most stable. Now, again, they can do this by doing numerous different things with their electrons. And depending on what they do with the electrons, whether they share them or trade them, there are different types of bonds that can exist. So the different types of bonds include ionic bonds, covalent bonds, and hydrogen bonds. Hey, we're going to look at all of these in detail, but just to introduce them right now. An ionic bond is literally just a bond between ions. Okay, a bond between ions. And an ion is a charged atom. Remember, we said that at the start, atoms are neutral, right? They don't have a charge. The positives and the negatives cancel each other out. Well, atoms don't have to stay that way. They can take extra electrons or they can give electrons away. And then the positives and negatives don't cancel each other out anymore. And you have an atom that has a charge, right? A charged atom is an ion. So when we have two ions that are attracted to each other, that's an ionic bond. So an ionic bond is the attraction between cations and anions. A cation is a positively charged ion. So if the atom has a positive charge, we call it a cation. The reason it has a positive charge is because it gives away electrons. Okay, it's an electron donor. Just roll with me. We'll talk about this in detail in a sec. Anions are negatively charged. They have a negative charge because they've accepted extra electrons. So they have more of those negative electrons. So overall, the atom is negative. It's an anion. So if I have an atom right here that's positively charged, and I have an atom right here that's negatively charged, these opposites are attracted to each other, right? It's not just in dating. Opposites attract. Like a magnet, right? When you have opposite sides of the magnet, they pull to each other. Magnets are created by pulling all the electrons to one side of the metal, or one side of the magnet. So when you have an atom that's positive and an atom that's negative, those opposites attract, and that holds those ions together. That's an ionic bond. Now I have this larger structure. Instead of two separate atoms, I have something bigger. A covalent bond is a strong bond that occurs when we have two atoms that share electrons with each other. Okay, so they come together and nobody gives away an electron, nobody takes an electron, they just share them with each other. Hydrogen bonds are bonds that are based on partial electrical charges. So instead of having a completely instead of having a completely positive charge and a completely negative charge, you have a part of a molecule that's a little bit positive and a part of a molecule that's a little bit negative, and so there's a little attraction between them. This is not going to make any sense right now because you don't know what a polar molecule is right now. But eventually we'll get to that and it'll make sense to you. Okay, so let's just keep going for now. When chemical bonds join atoms together, they form larger components, right? So instead of separate atoms, we have something bigger. That something bigger is either a molecule or a compound. So technically the term molecule and the term compound can be describing different things. A molecule exists when two or more atoms are joined together by strong bonds. I don't care, you can cross off this strong bonds part and down here this strong or weak bonds. I'm not worried about getting into it that in depth. Again, it's not a chemistry class. So a molecule is just when two or more atoms are joined together. It doesn't matter what the atoms are. It can be two atoms of hydrogen. So if I have one hydrogen and it's bonded to another hydrogen, that's two atoms, so that's a molecule. Compounds are two or more atoms of different elements. So that means that in order for it to be a compound, there must be at least two different elements. Right, or two different types of atoms. So this right here, where I have a hydrogen bonded, like sharing electrons with another hydrogen, that's a molecule, but that is not a compound because all I have is hydrogen. I don't have two different elements present. Okay, if I had water, right, H2O, that's a hydrogen and another hydrogen, but I also have an oxygen. Right? So if I have H2O, that would be a compound, right? I have two or more atoms. There are three atoms, and I have multiple elements. I have oxygen and I have hydrogen. So H2O is a compound. Do you think it's a molecule? Yes, it's also a molecule. It has at least 2 atoms, so it's also a molecule. According to that definition, all of the compounds are also molecules, right? So if it's a compound, it must have 2 atoms, so it must also be a molecule. But not all molecules are compounds. Okay, so the 2 hydrogen up here, this was a perfect example. That counts as a molecule, but it does not count as a compound. So make sure you're comfortable with this. So if I give you, whatever example, make sure you can tell me, is it a molecule? Is it a compound? Is it 1 atom? What is it? So if I said O2, that means that I have 1 oxygen bound to another oxygen. Is that a molecule? Yes. Is that a compound? No. Is that an atom? No, it's 2 atoms, right? There are 2 oxygen there. If I have C6H12O6, you'll see that a lot because that happens to be the chemical formula for glucose, and we talk about glucose, sugar, a lot. But that means there are 6 carbon, 12 hydrogen, and 6 oxygen all bound together. Is that a molecule? Yeah, there's at least 2 atoms. Is that a compound? Yeah, there's more than 2 atoms, and there's 3 different elements. There's carbon, hydrogen, and oxygen. Okay. Is that an atom? No, that's a lot of atoms, right? That's 24 atoms. What about carbon? Is that a molecule? No. Is it a compound? No, that's an atom, right? It's just 1 single carbon. It's just 1 atom. Okay, so we know that atoms interact with each other by forming bonds. And when they do this, they form larger units called molecules or compounds. We know that the way atoms do this, the way that atoms form bonds, is by utilizing their valence electrons, right? Their outer electrons. And the reason that they do that is to try and fill up their outermost shell. They want a full valence shell. So now we're going to talk about those different types of bonds that occur in more detail, right? We said ionic bonds, covalent bonds, and hydrogen bonds. We'll go through each of these in quite a bit of detail. So we'll start with ionic bonds. I said that ionic bonds are bonds between 2 ions. Makes sense. And an ion is just a charged atom. So this is an atom that's not neutral. It's either positively charged or it's negatively charged. That must be, in order for it to be charged, the protons and electrons have to not be equal, right? Remember, when protons and electrons are equal, they cancel each other out. But if they're not equal, right, if the positive charges and the negative charges are not the same, then you end up with an ion. You end up with an atom that has a charge to it, either positive or negative charge. So when we have an ionic bond, we end up with a positive ion and a negative ion, and the opposites attract. So in an ionic bond, what happens is we have 2 atoms come together, right? And they're both trying to fill up their outermost shell. One of the atoms, which we call the electron donor, because he's going to donate electrons. He's going to give electrons away. This guy loses 1 or more electrons. Now, because he's giving away those negative charges, he ends up becoming a cation, meaning he ends up having a positive charge. Hey, think about it. If you started out neutral, if I started out with 6 protons, which are positive, and 6 electrons, which are negative. I started out like that, and I gave electrons away. Say I gave 1 electron away. So now I only had 5. Now I have 6, plus 6 minus 5. Overall, that's plus 1. That's positive. So overall, that atom would have a plus 1 charge because he gave away those negatively charged electrons. Okay, again, a positive charge makes something a cation. If you write the word cation, look, it has a big, it has a big positive in the middle. Right? Cation. Right? Cations have a positive charge. So you've got an electron donor, and then the other atom is the electron acceptor. He takes those electrons that were given away. And because he's taking those negative charges, now he's going to have more negatives, and he's going to become an anion. Anions have an overall negative charge. Okay, again, because they have more electrons. Then I have two atoms. One's positive and one's negative, and opposites attract. So they're pulled together just like a magnet, and those two atoms are held together like a magnet, forming an ionic bond. So here's an example of an ionic bond forming between two atoms, a sodium atom and a chlorine atom. And this forms something called sodium chloride. That is table salt. So when you put salt on your food, this is what you're putting on your food. The reason the sodium and the chlorine attach to each other is because of their valence electrons and because they form an ionic bond together. So this shows us like how they start. Okay, so when we have two atoms and they have not interacted with each other yet, this is what they look like. So let's start with sodium. Sodium is up top. The symbol for sodium is Na. I don't know why, but that's it. So Na is sodium. You should memorize that because we'll talk about sodium a lot, and I'll always write Na. I won't write out the word sodium. So sodium is atomic number 11. Okay, so think about, what does that tell us? That tells us it has 11 protons, which are positive, and 11 electrons, which are negative. Let's place those electrons. Okay, we have 11 electrons to put in the shells. How many go in the first shell? 2, right? So you see these, there's 1 and 2. Then the first shell's full and I have to go out. How many can go in the second shell? 8, right? So you see 1, 2, 3, 4, 5, 6, 7, 8, right? So that's 10 that we've put in there so far. We have 1 more. So we have to go out to the third shell. So this third shell out here has 1. How many can we put out there in the third shell? We can put 8. Right? So sodium has 1 in this third shell, and it really wants a full valence shell. So it either has to take 7 electrons from something. That's just not going to happen. No atom is going to give away 7 electrons. So it's never going to be able to take 7 electrons to fill up that third shell. The other thing that the sodium can do is give away this 1 electron. It only has 1 measly electron out there. If it gives that electron away, this third shell disappears. Remember, there are not going to be empty shells. So if there's not that 1 electron anymore, this third shell goes away and the sodium looks like that. And now if you look at this second shell, it has 8, it's full, that's now happy. So that's exactly what happens. The sodium donates an electron, gives an electron away. So if you look over here at the second picture, now this sodium still has 11 protons, right? That never changes, but now it only has 10 electrons. So it's not balanced anymore. Now there's more positive charges. So overall, this sodium has a positive charge. It's not a sodium atom anymore, it's now an ion because it's charged. So you see next to the symbol it has this little plus sign, and then you look down here, notice we wrote this little plus sign because it's now positively charged. Now, is that an anion or a cation? Hopefully you said cation, right? Sodium is a cation. It is positively charged. Now, let's do the chlorine, okay? If you feel comfortable just doing this process with the chlorine right now, go ahead, pause the video and do it. You don't have to, like, you can try it to see if you can talk through it yourself, or you can go through it with the video with me. Chlorine is atomic number 17. That tells us it has 17 protons and 17 electrons. So let's place those 17 electrons. 2 can go in the first shell. 8 can go in the second, right? So that's 10. That leaves us 7 more to put in the third shell. So chlorine has 7 in this third shell out here, and it can hold 8. So chlorine is dying to get one more electron, right? It's like it's so close to having a full valence shell that just as much as sodium wants to give one away, chlorine really wants to take one. So they're like perfect for each other, right? They're a perfect match. So that's exactly what happens. This electron that sodium was giving away, it gives it to chlorine. Chlorine's happy to take it on. So if you look over here, this is what chlorine ends up looking like. Now it has 8 electrons in this third shell, which means the shell is full and he's happy. However, now he has 18 electrons, right? Still has 17 protons because that's never going to change, but it has 18 electrons. So it's got more negative charges. So if you look here, we say that this is negatively charged. And down here, instead of having a chlorine atom, we have a chloride ion, right? And next to the symbol of Cl, we have this negative because it's negatively charged. So now it's a chlorine anion. So sodium is the cation, chlorine is the anion. And opposites attract. So now these two ions are held together because of this attraction between the positive and the negative charge. And that gives us this, sodium chloride. So that's an ionic bond. So now we'll go through covalent bonds. A covalent bond occurs when there is sharing of pairs of electrons between atoms. So instead of having two atoms and one just gives the other one electrons, neither one of them wants to give anything up. So instead they come together and they share pairs of electrons. They can share 1 pair, 2 pairs, 3 pairs. When they share electrons, 1 electron is donated by each atom to make that pair. So if 2 atoms come together and they're going to share a pair of electrons, this guy will donate 1 electron and this guy will donate 1 electron, and then they share those 2 together. If they share 1 pair of electrons, we refer to that as a single covalent bond. We draw it with 1 line. So like H, 1 line H. That's telling us that these 2 hydrogen are sharing 1 pair of electrons. They can share 2 pairs of electrons. That's a double covalent bond. So like carbon with carbon. So each of these lines is representing 2 electrons. 3 pairs is a triple covalent bond. That's not really common in the human body. We're really just going to look at the way that a single covalent bond is formed, and that's fine. Just understand that double covalent bonds and triple covalent bonds do exist. All right, so here we see some covalent bonds. The first one here, don't worry about these. I just want to kind of show you really simply how this works. The first one here shows you H2, right? That just means that there are 2 hydrogen bonded together. And this here, you see H and then the 1 line and then another H. That 1 line is telling you that there's a single covalent bond. that those two hydrogen atoms are sharing one pair of electrons with each other. Now, if you think about hydrogen, remember, each hydrogen has one electron. So he has his nucleus in the middle like this, and then his first electron shell has one electron in it. And remember, that first shell holds two electrons. So they both, if I have two hydrogen atoms like this, they both really want one more electron, right? So this guy can look at the other one and be like, hey, give me yours. And then he's like, no, you give me yours. So instead of one of them stealing it from the other, it's better if they just come together and share what they have. And this is what ends up happening. They fuse their electron shells together, okay? And then they have two electrons that are able to move through anywhere in that area. So this one over here, this guy is like, hey, I've got a hold of two electrons in my shell, I'm happy. This guy over here also thinks, hey, look, I've got two electrons in my shell, I'm happy. Okay, remember, these electrons are moving super fast, right? They're moving all around through these shells really, really rapidly. So both atoms think that they have those electrons. Both atoms are happy. And because of these fused shells, they are attached to each other. They are held together because of that covalent bond. Now, there is no charge involved. There's no change in the charge because the protons and electrons still balance out, right? I still have one positive right here and one positive right here, one negative and one negative. So they still balance with each other. Now, we'll talk about, as we go forward the next few slides, I'll talk about how sometimes these bonds can be a little bit unbalanced as well. But in this case, they're completely balanced so that there's no charge involved. This is showing us a double covalent bond with oxygen when we have two oxygen atoms. And the only difference there is instead of only sharing two electrons, they're sharing four. So there's one pair and then there's another pair that are being shared. So each of these oxygen feels like they have 8 electrons in this second shell, right? This guy has 1, 2, 3, 4, 5, 6, 7, 8. So he's happy. And then the same thing with this one over here. He has 1, 2, 3, 4, 5, 6, 7, 8. They're just sharing more electrons in this case to try and fill up their valence shell or their outermost shell. So these are covalent bonds. Now, there are actually two types of covalent bonds, right? Covalent just means that the atoms are sharing electrons with each other. Now, they can share equally, where they both kind of have equal custody of those electrons, or they can share unequally, where one of the atoms is kind of like a big hog and he holds on to those electrons for much more time than the other guy. And they result in two different types of molecules. And this concept is very important as we go through anatomy and physiology. So kind of pay attention. If you need to take a break first, do it. So a non-polar covalent bond happens when there is equal sharing of electrons. And this forms a balanced molecule with no partial charges. So this happens anytime you have two of the exact same atom sharing electrons. So if I have two hydrogen, right, they're the same size, the same strength, so they pull on those electrons the exact same. It's perfectly balanced. O2, right, two oxygen, they're the same. This also happens when I have, I'm going to write it up here, when I have long hydrocarbon chains. So for example, in a lot of molecules in the body, you'll have like carbon, 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 and they're surrounded by hydrogens like this. Okay, and when you look at this, you can kind of see like how perfectly symmetrical it is. But those are all non-polar covalent bonds. There's equal sharing. The molecule is completely balanced. There's no charges whatsoever. It is non-polar. A polar covalent bond exists when there is unequal sharing of electrons. So in this case, you have two atoms sharing electrons and one of them is a hog, right? He's a bigger, stronger atom. He's more electronegative. He hangs on to those electrons for much more of the time. That means that the negative charge spends way more time over in this area than it does in this area. So you end up with a molecule that's what we call polar. It's not balanced. It has a negative pole and a positive pole. Now, these are not ions, right? It's not a complete positive and a complete negative. It's just a partial positive. It's just you have this molecule, this large substance, and there's an area that's kind of negative and there's an area that's kind of positive. Okay, there are lots of examples of molecules that are polar. Glucose, for example, sugar is a polar molecule, but the classic polar molecule is water, okay, or H2O. Whether or not a molecule is polar or non-polar is going to be incredibly important when we talk about its behavior. Okay, so this is an important concept. Polar just means the molecule is not balanced. It's got kind of charges present in it. Non-polar, like fats are non-polar, that means there's no charge. So let's look at water and see, why is water a polar molecule? Why does it have polar covalent bonds? Water is just H2O, right? We've got oxygen, and oxygen has 6 electrons in this second shell. So it really wants 2 more electrons. And then we have our hydrogens, right? 2 hydrogen atoms. This hydrogen over here has 1 electron, right? And it really wants 1 more. So it'll come and it'll share a pair of electrons with the oxygen, right? And that gives us this bond here. But that makes this hydrogen happy because he's got his electron, and oxygen's gotten 1 more, but he's still not done. He needs another one, right? Then he only has 7 of 8. So he needs another hydrogen atom to come on in. And so this hydrogen then gives another electron as well. So you see that the oxygen is sharing electrons with a hydrogen here and a hydrogen over here. Now, just looking at that, you can see that oxygen is much bigger, right? He's a much bigger, stronger atom. He has a lot more of these positive protons in the middle that are going to pull those electrons over, right? So the electrons spend way more time over here than they do over with the hydrogens. That means that there are negative charges present on this side more than on the other side. So that creates a polar molecule. Parts of it are kind of negative. That's what this sigma sign right here means, like partial. So there are 2 partial negatives over here. And then each of the hydrogens is like a little kind of positive zone. So there's a partial positive over here by the hydrogen and a partial positive over here by this hydrogen. So water is polar. It has partial charges present. Now, the reason that that is important is because that allows polar molecules that have partial positives and partial negatives. They allow for us to go to our next type of bond, which is a hydrogen bond. A hydrogen bond is the attraction between the slightly positive and slightly negative portions of polar molecules. Because remember, opposites attract, right? That's how the ionic bond works. We've got a positive and a negative, and opposites attract. Well, with a polar molecule, it's not a full positive and a full negative, but it's still kind of charged. So the whole molecule can arrange itself so that the negatives are by the positives of another one, right? And then the positives by the negatives of another one. And you form these slight attractions between the molecules. Those are hydrogen bonds. So if you look here, you see a bunch of water, and you see that the water molecules have arranged themselves so that there's attraction between the positive and negative parts of the polar molecules. So like if you look at it, this is the positive part, right? The hydrogen that's kind of positive. And it's arranged itself so that it's close to the negative oxygen, right? And then over here, this positive hydrogen has a slight attraction to the negative oxygen, right? This positive hydrogen has a slight attraction to the negative oxygen. So they're not like full bonds with each other, but there is a slight attraction here between these partial charges, these opposites. Hydrogen bonds between water molecules are the reason that water behaves the way that it does. And this is really the reason why life exists. Water is incredibly important in the behavior of, or life really, and our bodies are made up of mostly water. And the reason that, for example, sweat cools us off is because of these hydrogen bonds. The reason that salts and sugars go into solution, they dissolve in our bodies, is because of these partial charges, the polarity of water. So the fact that water is polar is very, very important to its behavior. Hydrogen bonds between water molecules happen to be the reason for surface tension. So like if you see a water bug walk on the surface of water, right? The reason that he can do that, or like a leaf, the reason that a broad leaf floats on the top of water is because the water molecules are attracted to each other and they don't want to separate from each other. There are hydrogen bonds holding all the molecules together. So it takes a certain amount of force to push through and break that bond. Obviously, I can easily break the bond to push through the water, but there is a slight attraction there. That's why, like, if you've ever filled up water to the very top of a cup, it will actually go higher than the rim before it pulls over, because the water does not want to separate from the other water molecules. There are slight hydrogen bonds present there. These last few slides, you guys, are just examples of different like chemical notation. So just the symbols that we use when we're writing out, chemical formulas and whatnot. So I do recommend that you just kind of read through this on your own a little bit. This is just like, for example, if we have one hydrogen atom, we just write the symbol, an H. If I have two hydrogen atoms, notice they're separate. It's not two hydrogen bonded to each other. It's two separate hydrogen. Then we write the number 2 before it. So that's telling me I have two hydrogen. I've got one here and one here. If I wanted to tell you that the hydrogen were bonded together, that it was a molecule, in that case, the 2 would be a subscript like this. Okay, so that's, yeah, right here. When the two hydrogen are bonded and it's a molecule, then the 2 is the subscript. Okay, or like this right here means there are two hydrogen and one oxygen all bound together. Okay, if they were separate, I would put 2 hydrogen, right, and then plus 1 oxygen. Those are all separate from each other. But when it's written like this, that means that they're all bound together. This is just showing you a reaction. So for example, 2 hydrogen plus 1 oxygen, all separate, which you see here, If they all join together, right, the arrow is showing me where it's going, they all join together to form H2O, water. Equations have to be balanced. So there has to be the same number of atoms on each side. Like atoms don't just disappear. So for example, over here we have 2 hydrogen and 2 oxygen. Well, look over here. We only have 1 oxygen. It's like, what happened to the other oxygen? You have to account for it in some way. Atoms don't just go away, or they don't just come out of nowhere. So equations have to be balanced on either side. And then finally, ions. If something has a charge, we put it up here, superscript up at the top. If there's just the plus sign, that means it's 1 positive charge. If it's just the negative sign, that means it's 1 negative charge. If it's more than 1, we put the number. So 2+. Calcium, for example, is a cation with a 2 charge, a charge of 2 positive charges. Sodium only has 1 positive charge, so it just has the plus sign. I'm going to leave right here. I'll start the next lecture with this slide because I have taken up every last second of our hour and 20 minutes together. So we'll start the next presentation with this slide right here. If y'all have any questions, please feel free to shoot me an email, and then I'll talk to you tomorrow. Bye. Have a good day.